lambda paradigm, so-called, I'll call them for the purpose of this talk, conventional quantum liquids. And these are, familiar to this audience. And last week, much of this was discussed. For example, toric code, spin ice, and various other models that emerge to try to understand states of matter that don't break symmetry, but nevertheless have non-trivial. And so here's a list of some sort of typical properties that these systems have, and what's true is, in addition to topological order and ground state degeneracy, long-range entanglement, they're all fit quite well into a description, a gauge theory-like description. Okay. I would say, the experimental realizations of these are still sorely missing, except for, things like fractional quantum Hall effect. But what's true that in the last, maybe 20, 25 years, we now know for sure that there are models that exhibit this behavior. It's not just kind of a hand-wavy approximate statements about potential realization, but it's really, there's models, even if contrived, some are contrived, but some are, like the story code is a pretty concrete model which does exhibit this kind of behavior. And so this is, okay, so a lot of the focus is try to not only explore these models and think of new ones, but also figure out how to probe them and to search for this kind of order. But moving on in the level of complexity, and therefore maybe sadly sometimes moving away from reality or experimental realizations, is the subject of fracton matter. And these are these strange quantum liquids that have restricted mobility, and you heard a little bit about it in Fiona's lectures last week. So they're the kind of models one has here. And so in general, there's not simple physical realizations of these things, although my message of my lecture will be that there are, as I already stated in the opening of the talk. But the models are extremely sophisticated and very elaborate, and they sort of fall in two classes. They're discrete lattice models, sort of like the toric code, but with higher body interactions. And then there's gapless tensor gauge theory-like models. So these share a few common features. They have exponential rather than finite number degeneracy that scales with system size and often in an exponential way, but also often depends on the size of the system. So and this is an example of where sort of short-scale physics matters and never goes away. So the lattice and lattice structure matters. There's no immobility, means there's no deformable string operators like there is in lattice gauge theories. And I already mentioned there's this UVIR mixing. So in a sense, we're still trying to understand them. And I'll present gauge theory, certain kind of gauge theory formulation of these, which are relevant, which naturally appear in the context of crystals. But so they capture some physics, for example, immobility, but they're certainly failing, to capture some of these other features, and therefore one could say that this phenomenon is still to be understood and somehow lies beyond standard Q of T. So one simple way to encode this restricted mobility is by enlarging the conservation laws to enlarge standard charge conservation to a multiple conservation, where now some higher moments of charge density. Yeah, this is the problem I'm going to from Mac to Microsoft. Anyway, so sorry about that. So there's a dipole. In addition, you can incorporate dipole moment conservation in addition to the charge conservation. And a simple way to do that is to simply consider currents, which are themselves the higher derivatives of a tensor, of some kind of a tensor, higher tensor current. That will automatically guarantee a structure like this will automatically guarantee that n moments of charge density are conserved. Okay, so that's kind of the simplest way, and there are realizations of this kind of higher moment theory multiple theories, and for example, a tilted potential, if you have a particle moving in the tilted washboard potential, as was studied by Bakar and company, there's an energy conservation. So because of the energy conservation, a particle by itself can't hop. If it hops uphill, it doesn't have enough energy, it'll be off resonance. Downhill, it's also off resonance. So, but if two particles, one hops in one direction, one in the other, then this two particle process, and that's a hopping that's allowed. That's a dipole conserving process. Lowest Landau level guiding center hydrodynamics turns out encodes this kind of a dipole symmetry. In fact, composite nucleus 1/2 fermion is a dipole, so there's a way to think, is a neutral object, and it's a dipole, so there's a way to think of properties of a composite Fermi liquid as this kind of a dipole, having this dipole conservation. And another example is the quantum vortex liquid, is what I'm going to talk about. But I'll also take this opportunity to mention an ancient paper in collaboration with Liam Balentz, going back to '96, probably most of you were not born, where we studied actually, in fact, melting of a vortex lattice, something that I'm still work on, although much of the focus now is on quantum version of that. And, in the lowest Landau level, so there you basically trying to understand HC2 transition, which really beyond mean field theory, HC2 transition is a melting or freezing transition of vortices. And so there, let's say you work in 2D, you lose the dispersion completely once you're in the presence of magnetic field, because you're now within the lowest Landau level. So then all that's left is the interaction term. And what we were able to show is that, in fact, that interaction term is just the hopping, is this dipole conserving hopping. And that's because these site operators, think of Landau gauge, are actually also momentum operators. They label momentum, and so the reason you can't hop is because of momentum conservation. For example, the two particles, if they want to hop, they have to hop in pairs, such as to conserve, along the x direction, such as to conserve the y moment, the y momentum, okay? Because this has higher linear momentum along y than this one. And similarly, hopping in the y direction has to be in pairs because it's forbidden by x. Anything else is forbidden by x momentum conservation. And so you literally get this out of the quartic interaction of the Landau theory. And so we noticed this before, but we didn't appreciate that this whole world opens up when you start thinking about models like this. But okay, and one can, starting with kind of a Hamiltonians like this, one can go to a field theory, and lo and behold, the kind of a field theory and continuum limit is these Lifshitz-like models, high derivative models. And they have, in the continuum, they have this dipole U1 conservation where you can change the phase not just linearly, not just by a constant, but by a linear function of coordinate. Another type of symmetry that's even more, if you wish, contrived, or more fine-tuned, if you wish, is the subsystem symmetry where, for example, 2D, on every row and every column, charge density is conserved. Charge is conserved. And so these quantities are conserved on every x and y row. And this is so-called foliated charge conservation. But under the old name, this was, to my knowledge, first was studied by by a model, a ring exchange model by Permacanti, Balentz, and Fisher. So one can think of this as a plaquette XY lattice model that they considered, and this is just, you disallow by hand single particle hopping, and you only allow these ring exchange-like hopping that automatically has this symmetry. In the continuum, it also looks like a Lifshitz model, but a plaquette version of that, where it's not just a second derivative, it's a second derivative, but in this very special XY-like way. And so that encodes the subsystem symmetry. So now there's a two U1s, there's a Lx plus Ly U1s, one arbitrary function at every row and every column. Okay, but moving on to more and more complicated models, it turns out that if you take one of these plaquette-like models, but in the simplest case, as it was done by Vijay, Ha, and Fu, if you take plaquette Ising model instead of plaquette XY model and gauge it or dualize it, what you get is this X-cube model, fractonic X-cube model. So And so this is a theme. You can take subdimensional, like these subsystem symmetries, and gauge them and get fractonic models. And then there's, slew of activity that's came up with all kinds of constructions, and most of them I can't keep up or even understand, so they're beyond me. But I will give you just one corner of this, a little corner of this, that one that's the higher rank tensor gauge theory that was introduced by Michael Pretko in 2016 as a PhD student at MIT. And these theories come with a generalized Gauss's law, which is a double divergence from the electric field, which is a symmetric tensor, rank 2 tensor, hence higher rank tensor gauge theory. And of course, there are generalizations of this, and there's various versions of this. I'm going to give you the plain vanilla version that comes up, and it will be relevant to what I'm going to discuss. It's called scalar charge, so that means this is full divergence on both indices, and this guy's a charge is a scalar. So the upshot of this is that if you consider these kind of tensor gauge theories, then this double divergence encodes automatically that the charges that appear on the right-hand side are actually immobile. So this kind of Gauss's law, generalized Gauss's law, encodes the fact that dipoles are conserved and therefore particles cannot hop. So a charge cannot move because the motion of a charge is a creation of a dipole. So it's as simple as that, and this is this brilliant idea by Michael Pretko. I was lucky enough that Michael then came to Colorado as a postdoc, and just coincidentally, I was at the same time working on trying to I was intrigued by this idea of immobility or restricted mobility, and realized, or at least had this conjecture, that topological defects in the crystal also seem to have this kind of a well-known, at least for dipoles, namely dislocations, have this kind of a restricted mobility. And and I was exploring that when Michael came to Colorado, and so then we teamed up, and we were able to show that in fact there are physical realizations of these tensor gauge theories, and they very naturally sit, and I realized, in conventional quantum crystal. So think of a crystal, balls and springs, but P and Qs don't commute. So there's a strain tensor squared, that's the elastic energy, there's kinetic energy, and then what you consider is the topological defects in this kind of a lattice. Okay, dislocations, disclinations, which I'll discuss, and the idea is that, the upshot is that this guy is a dual of the tensor gauge theory. Okay, so these are the topological defects. You can have rotational defects. So I'm considering 2 + 1 dimension for simplicity. So these rotational defects that are called disclinations. There are dislocations, and this is the thing that kind of set me off on this conjecture. It's a well-known fact that dislocations are, if there are no vacancy interstitials, dislocations can glide, as illustrated here, but they cannot climb. Okay, and according to this conjecture, there's this predicts this relation to the fractons is, as I will discuss, these disclinations are in fact, you would predict that since dislocations are dipoles of disclinations, these disclinations will be immobile. And this is something that, to my knowledge, was not, while this fact was a common knowledge in elasticity theory and theory of defects, this was, if you wish, a single, one product I can point to that from the fracton physics, this is a prediction for elasticity or theory of defects, that the disclinations in the crystal cannot move. Okay, so then this is the tensor gauge theory formulation. I already mentioned this. So it has a standard Maxwell-like Hamiltonian. There's magnetic field, electric field. These are derived from vector potentials, except they're not vector potentials, they're tensor potentials. B is some kind of a funny curl of the reg 2 symmetric tensor potential. And E is a time derivative of the scalar A0 component, and a double derivative of the scalar potential and time derivative of a tensor potential. Then there's this Gauss's law for these charges, and then there are dipoles that have some mobility but have a restricted mobility. There's a Faraday law that's written like this for this tensor gauge theories. Now, what Michael and I were able to show is that standard boson vortex duality, or mapping an XY model to a 2 plus 1 dimensional XY model to a abelian Higgs model, all those, same name for the same duality. If you just generalize that to this kind of a tensor gauge theory instead of a vector gauge theory, or maybe going from here, in disguise, one can think of this to the extent that Uij is a strain tensor, and therefore it's a derivative of a Goldstone mode. Much like in the XY model, you have a gradient of phi squared, which is the kinetic energy. This is just, roughly speaking, an extra index XY model for each of the UX and UY phonons. So if you squint your eyes, then this is just a boson vortex duality between this guy and this guy, where defects, for example, dislocations of this theory, become charges at dipoles of this theory. It's as simple as that. Where, in contrast, in the XY model, you have just vortices mapping onto particles in this theory that are gauged under this theory. Okay, just some cute observations. Faraday effect is nothing more than Newton's law. Oops. I can't even see. Okay, so the Lorentz force just becomes a famous Peach-Cola force on the dislocation. Yeah. So this is very natural in 2 plus 1 dimension. In higher dimensions, this is something Michael Pretko generalized a year later after our paper, and it's, you get a theory, how should I say it, where, let me think. So your gauge theory ends up having, it's the gauge field is both symmetric tensor and it's a higher form. It's much like if you take an XY model in 3 plus 1 dimension, you get a higher form gauge theory. Okay, so that's what happens. And let me think if there's anything else I can say about it. Yeah, I'll just leave it at that. Yes, yeah, it's abelian. Okay, so a few other cute things that comes out. If you look instead at the Ampere's law, d dt, curl of B is, in this case, a trace of J. J is a tensor, so trace of J. This turns out to be a glide constraint between vacancy interstitials. So, in other words, if you have vacancies interstitials, their continuity equation, which is written here, is violated by a climb of dislocations. So if dislocations climb, they kind of create a tear, and they create vacancy interstitials. Another way to say it is, the only way, the other way, if you read in the other direction, the only way to get this climb, or dislocations to climb, is to allow some vacancy interstitials to eat up that climb, okay? And this, in fact, we noticed with Christina Marchetti thinking about vortex line liquids and crystals and their phase transitions, which I'll mention at the end, hopefully. So we derived this thing without any dualities, but just thinking about vortices and their dynamics in the presence of vacancy interstitials, all the way in 1999. So it was very nice how this actually very nicely, compactly incorporates this physics. Okay, so now to the subject. How much time do I have? 20 minutes, maybe? Yeah, so that's the full time, right? So that's 45 minutes. Okay, wonderful. I'm in good shape, I think. So yes, I want to talk about rotated superfluids. So in some sense, everything I said so far, the rest is no surprise, because you rotate bosons, they'll make a vortex lattice. Vortex lattice is an example of a lattice that I talked about. It's kind of it's a lattice that breaks time reversal symmetry, but nevertheless it's a lattice. So therefore you can start thinking about dislocations and disclinations and vacancies and interstitials in that lattice. So much of what I'm going to say what I said so far is going to be also applicable. And so in some sense, it's some details that are interesting and new because it's a different kind of lattice. And I want to contrast, and I'll hit on those points again, contrast it, for example, from, well, conventional lattice that I already discussed, but another kind of lattice of, for example, Wigner crystal, which will be different than a lattice of vortices, okay? And, you know, in an interesting way. So just a little bit of background. So this is completely sort of, in some sense, standard, but maybe not at most of you fingertips. You know, thinking about rotated superfluids goes back to Ansager, Feynman, and Witten. So the kind of general theory is well understood. So here's the sort of a Gross-Pitaevsky-like description. You go to a rotating frame. So you go to a frame rotated with capital omega, that couples to LZ. You can think of it also, this is just the chemical potential for LZ because you want to consider states at finite angular momentum. In this mapping to a gauge theory, this actually, or to mapping to background magnetic field, this term actually can be interpreted as just a vector potential dotted into a particle current, boson current. And that's because this is omega, LZ is V cross R. But so if you associate cross R with omega, then that becomes a vector potential, it becomes B cross R. So this looks like a vector potential times the current, V, okay? Okay, so it breaks parity in time reversal, so you have a Hall response over these vortices. Okay, in the London limit, maybe this is maybe constructive. This is the kinetic energy. When you go to the ordered state, this is the momentum, and this is the what happens to omega. So this is the vector potential that I mentioned. Okay. Actually, as an aside, I'll mention that in 2004 with postdoc Dan Sheehy, we were intrigued by a following observation. You know, when you rotate these vortices, rotate these superfluids, condensates, as Eric Cornell did, you know, they're in a parabolic potential. So naively, if you're a condensed matter physicist, as we are, I would say, you know, you would have asked me, and at least first naive expectation is that it's not going to have a uniform density of vortices because, you know, you're rotating, and so then condensate is weakest at the edges. So you would think, why not put vortex where the condensate is where the hole in the condensate is cheapest? That's what happens why vortices are attracted to impurities, for example. They want to coincide the absence of superfluidity of the two objects, the impurity and the vortex. But in fact, if you look at these guys, they're extremely uniform. And that's in the end, we try to explain that, and that's in the end, if you wish, a correspondence principle. The thing rotates at, if you didn't distinguish, if quantum effects or discreteness of vortices is not important, the thing just rotates as a rigid body. So density of vortices is just proportional to omega. And so that means it rotates as velocity is just omega cross R. But there's a small correction coming from, so this is, that's the uniformity. And that's just a correspondence principle. In the high velocity limit, modular, and you go into quantum Hall and anything like this, it's going to be just a rigid body rotation. Okay. But then there's a correction from the non-uniform superfluid density. This guy is some kind of an inverted parabola due to the trap. And in fact, there's this correction that we found, which is a Laplacian of a log of rho S of R, which is the stiffness. And that comes purely from the discreteness of vortices. Okay, so one thing you learn from this kind of a description is that the energy goes as a log R, let's say in 2 dimensions, but this object goes as R squared. So in fact, you know, there's a critical velocity, but rotational velocity, but of course it vanishes 1 over R squared. But it kind of looks like the type 2 superconductor, except this guy vanishes. So if you rotate at some omega, in order to start getting some vortices, you need to overcome this omega, critical omega. And that critical omega, give or take, is basically you have to rotate such that over size of the sample of size R, you can put in 1 quanta of angular momentum. That's really what this says. H bar divided by moment of inertia mr squared of the whole sample. Okay, so, and this is what it looks like, and that's the correspondence principle I talked about. You put in all these vortices, on average, they give you this linear growth of the velocity as a function of R. That's just this statement. But then there are corrections from this discreteness. And then, you know, from that, you can just read off that or you can compare Coriolis force to the Lorentz force, and that's this connection between effective magnetic field and of the rotated superfluid. So effectively, it looks like you're in the magnetic field, which is omega times twice the mass. The boson current is just the density times the current, spatial current. So that's one part of it. And then this is described by just the XY model or interacting boson model of the superfluid. Here's the Lagrangian description of it. And then this superfluid component now develops vortices that are described by, some coordinate. In general, a vortex, they form a vortex lattice with some rest, some undistorted positions plus some phonon description. And, the simplest level is just what I wrote down before is just this is the kinetic energy of vortices if there's a mass, and then there's elastic energy in terms of the strain tensor. So there are these two sectors, the superfluid sector and this sector of the elasticity and kinetic energy of vortices, and one needs to couple them together, okay? There is, and that will come from the coupling, in fact, okay? So one may think you just write it down, but it's actually, you can see as in the next slide, it'll come from the coupling. Okay, so when you have an XY model like this, well, in fact, by duality, this is something, boson vortex duality of the vector gauge theory, to the ordinary boson vortex duality, the density maps onto the magnetic field, density and the current maps onto electric field, up to 90-degree rotation. So that means by duality, this Lagrangian, XY model Lagrangian, maps into E squared, which is this term, kinetic energy, and this guy is the magnetic field squared. But then in the presence of vortices, so in the absence of vortices, the Maxwell phase of this Maxwell Lagrangian is just nothing more than superfluid Goldstone modes. That's what it's encoding. But now, in addition, vector potential is sourced by the charges of this gauge theory, but the charges are just the vortices, defects in phi. So you have this J mu A mu term. And so, like for example, so in that term, actually, if you represent vortices in terms of a dual gauge potential, another gauge potential, A twiddle, this is just a mutual Chern-Simons term between the vortices and the bosons. Okay, so there's a description there that's of interest. But, more explicitly, so vortex lattice current is just a curl, space-time curl of a gradient of phi. It's really the non-single valuedness of phi that you're encoding. So that's the current. But it turns out, if you're in the crystalline state, and that's what I mean by this J. But if you're in the crystalline state where there's zeros, these vortices form a crystal, then it's actually can be written as this object. Okay, the intuition I can give you about this object is if you look at the zeroth component, namely the vortex density J0, this is just nothing more than a two form it's a pullback from the reference state to the actual state of the distorted vortex lattice. Or you can think of it as a determinant of the strain tensor between the actual positions of vortices and the reference state of vortices. That's the fluctuation term. That's right. There's also background one. That's right. That's what you were worried about. Yeah. So in general, there's also capital B, which is the proportional to omega. You're right. Yeah. So this current couples to this vector potential, and what you end up getting is now the two sectors are coupled together. The superfluid part described by a U1 gauge theory. This is the elasticity of vortex lattice, and then you have this J dot A term. And in fact, so that's what distinguishes this sector is what distinguishes it from this vortex lattice from a Wigner crystal. It's as I say here, vortex lattice quantum field theory is really a Wigner crystal plus this Goldstone mode, the superfluid Goldstone mode that's encoded in this U1 gauge theory. Okay. And to zeroth order, as I'll say, it's this A0 component of this superfluid component just gives you incompressibility of this vortex lattice. Okay. oops. So yeah, so this is where if you write if you write this perturbatively in the phonons, these currents, then you observe that, for example, Ji, the spatial component of this, has the velocity part, which I'll show in a second, and then that velocity part gives you A dot U dot, A times U dot, that's from here, and then it also gives you this fluctuation part of the non-commutative algebra of the phonons. You get U dot, so Ux is a canonically conjugate to Uy and vice versa. If you integrate out A0, you see A0 couples to JT. If you integrate it out, it'll give you incompressibility of the vortex lattice. And that's kind of the new feature of the that appears in the vortex lattice as contrast to the Wigner crystal. If you look at the equation of motion of this object with respect to the phonons, you recover in a very compact way the Kelvin's theorem. You get this equation of motion, but you can see here this guy is just a gradient of the stress tensor rotated by 90 degrees, and this guy is nothing more than velocity minus the boson current. So, and Kelvin's theorem just says that vortices, in the absence of any stresses, vortices move along the local superfluid velocity, okay? And they move accordingly if you modify that if you introduce stresses. So, so this is all very kind of a reality check or sanity check. Okay. So one thing one can do is one can solve this constraint very simply, incompressibility constraint, and simply write U as the rotated gradient of phi. And lo and behold, what one gets is a Lifshitz model with a Berry phase term. So this guy just becomes this funny Berry phase of this Lifshitz model. One can ask, what does this Berry phase do? Well, if phi is single valued, then you can just integrate by parts and it vanishes. But of course, if you have vortices, that integration by parts introduces vortex density. So what this term does is it tells you that vortex density is actually canonically conjugate to phi. So this phi just appeared as a resolution of this displacement, but as you will see, that phi is actually has an interpretation of the superfluid phase on top of the superfluid phase that's creating the vortex lattice. It's the extra phi on top of the deterministic phi that creates vortices. So you have the rest state, undistorted state of vortex lattice, that's a specific function of phi that has singularities at particular positions. Now you distort your vortex lattice, that creates a distortion in phi. It turns out that this phi, even though that's not how it was introduced, is the physical, that's its physical content. Okay, so from this you immediately get, never mind this thing, you get the famous Tkachenko quadratic mode, akin to a ferromagnet, and one can also study its width, and this was studied by Yincheng and Son and company, and they made a prediction that's omega cubed, which is inconsistent, or at least, how should I say, it's in contrast to the earlier predictions from, I think, Belyaev. I think originally the prediction was, well, I've forgotten what original prediction, but this is the prediction, and I don't understand this kind of a disagreement between, predictions from like 60s from Soviet Union and this latest prediction of the width. Okay. But the dispersion is this quadratic dispersion, and there's a single polarization corresponding to a single phi mode. Okay, so one can also make this match of the operators between the sort of the description in terms of elasticity and the Lifshitz model. Let's see. So now, in the theme of thinking about gauging or dualizing a theory with some global symmetry, but maybe higher multiple symmetries, like the Lifshitz model has, one can dualize this Lifshitz model. okay? And when one does that, one gets a traceless tensor gauge theory. So the tracelessness encodes the information of the incompressibility. So roughly speaking then, well, yeah, roughly speaking, this kinetic energy term, the higher derivative kinetic energy, just becomes the electric field squared. And the phi dot squared term, the interaction term, if you wish, for the boson, becomes this, magnetic field term, but it's coupled to the phonons, where this U, again, is an auxiliary field that appeared in the process of this dualization, but in fact, its role, physical role or physical meaning, is in fact the original phonon. Okay, so there's this U still coupled to the magnetic field through the density, and this is the Berry phase term that came from here. Okay, so there's a gauge redundancy that's natural. This is the mapping between the two theories in terms of operators. One can, as was sort of not showing here, there's a beautiful theory by Nguyen, Gromov, and Amoros in 2020 that instead of working through this Lifshitz model route, they started with the elasticity theory and dualized it using the kind of methods that Michael Pretko and I were using as well. And what they got is trace full gauge theory, rank 2 gauge theory that's given here. And it turns out that when you go to low energy limit of this theory, it reduces to this traceless gauge theory that we obtained from the Lifshitz model. Okay? Let's see. Okay, so there's some correspondence between the two theories that one can, well, even before dualizing. So kind of one may ask, why do you want to do this? What's the advantage? Well, the advantage is you're starting out with a theory that has the elasticity theory coupled to these Goldstone modes, superfluid Goldstone modes. And there's various symmetries. There's a U1 symmetry of the charge conservation described by this current in these conservation laws. There's also translations and rotations and their corresponding currents and charges. Well, in the Lifshitz model description, all those kind of go under a single enlarged symmetry of higher, dipole and quadrupole symmetry. So you get that the constant part of the phase shifts of the phase of the Lifshitz model corresponds to U1 symmetry, but then there's a linear and quadratic pieces, and that corresponds to translations and rotations. So there's much more kind of a unifying way of describing symmetries that appear in the original model. In this Lifshitz model description, it's kind of a more compactly realized with with this kind of a higher multiple conservation law, continuity equation. Okay, so this is summarized here, this relation. Okay, so there's some, algebra, anomalous current algebra on both sides of the mapping. One can think about topological defects of this Lifshitz model. So the Lifshitz model can have vortices, but it can also have dislocations. The dislocations are encoded by compactness of the linear in coordinate transformation of phi, and the rotational symmetry is encoded in the quadratic shifts in phi, quadratic in space shifts in phi. So for example, a disclination is you define an angle theta, which is the Laplacian of phi, and then you look at the non-single valuedness or winding of this theta field. This is the bond, physically this is just a bond angle of the underlying vortex lattice, and so a fourth derivative of this object, or a curl of the gradient of theta, which is a curl of a gradient of a Laplacian of phi, is the disclination charge. So if you solve this relation, you get this phi transforms like this, or has this configuration. A dislocation is just is a line and object, and it's just a dipole of these guys. So it has this kind of a form. for the phi configuration. And then there's also vacancy interstitials that are simply, they're violation, vacancy interstitial come in as a violation of compressibility constraint. So we had this constraint, divergence of U is 0, which in terms of phi is just a non-zero curl of a gradient of phi. If you think about a non-zero curl of a gradient of phi, physically means in addition to your vortex lattice, you introduce another vortex. Introducing another vortex is from the point of view of a lattice, is just introducing a vacancy or an interstitial. Okay, so that's the configuration that you get. Okay, so this is just a summary of that. So then one can look at also on the, yeah. You mean in Eric Coronel's images? Well, so that was an illustration of these Tkachenko modes. Yeah, so that was like an excitation. It's like a wave in this vortex lattice, and they studied dispersion of it, this quadratic dispersion of it, to the extent that you can in a finite system like this. Okay, so one can then, so far I've discussed the relation between elasticity of the vortex lattice plus this coupled to this superfluid Goldstone boson versus the Lifshitz model realization of all those, capturing that physics. So now one can also ask about, if you go to tensor gauge theory, this traceless tensor gauge theory by duality from the Lifshitz model, how those defects and how those symmetries realized. So not surprisingly, what one has is the winding one-form symmetry. So the current, one can define a current which is a symmetric rank 2 tensor. That's the density, that's the zero component of the current that's conserved, and that's just this double derivative of phi. And in terms of a gauge theory, it's just the electric field. And then the J, d phi dt is the current, scalar current, and that's the magnetic field. So there's a relation, which is the Ampere's law in terms of the gauge theory. It's time derivative of the electric field equals to a curl-like object of the magnetic field. Okay, so that's but one can, in terms of J's, it's just a continuity equation for rank 2 object. Okay, and then there's a Gauss's law on this zero component current, zero component of this tensor current, which is given like this. And in terms of electric field, it's just the Gauss's law. So those guys are symmetries or conservations in this tensor gauge theory. And so one can then think about corresponding charged operators in that gauge theory. And what they are the simplest guys are just, violation of this condition. So if you have a charge, so there's non-zero charge, you're violating this Gauss's law, so then this charge is the generator of this one-form symmetry. Okay, and so this guy then acts in the charged objects, which are just the Wilson lines. Wilson lines of the corresponding time component of the scalar potential. So these are the world lines, and these world lines actually describe nothing more than the vortex. These vortices, or these particles, are actually just disclinations. Okay, sorry to maybe super saturated with these relations, but okay, it's just a little bit of a matching game that we spent quite a bit of time trying to resolve. Yeah, so then once you understand the monopole excitations, violations of Gauss's law, then the dipoles are very easy. And these are just the vortex dislocation rather than vortex disclination, and that's just a pair of these with the opposite signs. So that's very easy to construct, and that's just a B cross X. That's what this charge is. So then the the generator of this symmetry is just the first moment of this charge, of this charge density, and that gives you the it's a Wilson line. It's a funny Wilson line, which is a derivative of the scalar potential A0. Okay, so that's the charged. This Wilson line is the dislocation, represents a dislocation. Okay, so then you can look at the quadrupole, and that's the vacancy interstitials, and this is summarized over here. I won't belabor this. So I'll conclude in the next few minutes by talking about melting, and so this brings me back to my youth. In the 90s, when high TCs were discovered, there were sort of two camps, aside from fragmented individual camps. There's a camp that focused on microscopics. That's the really important problem that's still unsolved. And the other camp that I was in is thinking about magnetic field temperature phase diagram. Basically, it's a type 2 superconductor that has vortices, so try to understand physics of those vortices. In contrast to low temperature superconductors, all of a sudden vortices in these materials come to life. It's kind of a whole new world of line liquids and crystals and hexadics, meaning you now have an opportunity to study statistical mechanics and dynamics of line objects, where your objects are not points but lines, fluctuating lines. Of course, underneath all this is some microscopic physics that gives you superconductivity. But if you're only interested in magnetic field temperature phase diagram, then its novelty and richness comes from fluctuations of these line objects. So then, so this is Abrikosov in 1957, but all of a sudden, beyond, once you go to high temperature superconductors and more generally, sort of novel high temperature superconductors, you get this kind of a picture where you have a crystal, but the crystal is now a fluctuating lines. Those lines can melt and give you some kind of a melted liquid of lines. So understanding these kind of phase transitions and in the presence of impurities, spinning and drive was a big sort of a theme from the late 80s to mid 2000s, and we've solved a lot of those problems. And so one of the things but of course, if you think of these as world lines of bosons, it brings us back to the kind of the subject of what I've been talking about. We're talking about vortices, point vortices in 2D, and this is sort of the z-axis is their time direction, absence of time direction. And so this is relic of that with Cristina Marchetti in one of the papers. We were studying melting of these vortex crystals. And so we thought about dislocation loops and how they can move. And this is something I mentioned, that we discovered that in particular, you can have a phase of matter which is where vacancies interstitials, which are line objects, proliferate. So you still have a vortex crystal, but that vortex crystal exists in the presence of vacancy interstitial lines. And these are the loops that describe those, these are dislocation loops. But if you also consider vacancy interstitials, then those guys can proliferate. But if you proliferate vacancy interstitial lines in this vortex crystal, you get a novel phase of matter, which is, the density of vortices is periodic, but it's no longer a superfluid, because vacancy interstitial lines, their mobility restores, destroys off-diagonal long-range order, okay? And it restores the U1 symmetry of a superfluid. So it's a kind of novel phase of matter. It's a vortex crystal, which is normal, okay? Unlike the quantum problem where, a supersolid of a quantum problem of bosons is a crystal of bosons, which is superfluid. Okay, this is a dual of that. Anyway, so we were enamored by that, and we derived this relation between vacancy interstitial continuity equation and dislocation tensor alpha ij. And in fact, this is the same as the no-climb constraint of dislocations for these kind of dislocation loops. So for what it's worth, we didn't appreciate the importance of this kind of a fractonic or de-restricted mobility physics. For us, it was just some weird example that came about thinking about this melting. And what comes out as a phase diagram of vortex supersolid, a hexatic, isotropic liquid, not just a standard HC2 phase diagram. So anyway, so you can translate those ideas to the quantum problem, zero temperature quantum problem, thinking about these guys as world lines of bosons. So you have a vortex crystal, you go to vortex supersolid, vortex hexatic, and a vortex liquid. And so how do you describe that? Well, that has a very nice and compact description in terms of this tensor gauge theory that I introduced. Here's the traceless tensor gauge theory. In its full, all you do is add matter to it, where that matter describes these dipoles, okay? And they couple it in a funny way. It's, this matter couples to not to the vector potential directly, but to some derivatives of the vector potential. Okay, amazingly, and it's very compact. You just go to the Higgs phase of this funny tensor gauge theory abelian Higgs model, and you discover that that you get to a state where the phase of this matter field of dislocations just completes it enlarges the degrees of freedom of this tensor gauge theory from traceless to trace full. So this tensor gauge theory converts into trace-full gauge theory, and that's the description of a supersolid. And in fact, this tensor gauge theory is exactly the one you would write down by looking at the Wigner crystal. So it all kind of hangs together very nice. You can think about defects in that, Wilson loops in that, which are disclinations. But I've spoke too long, so let me just summarize. I gave you some background information on the fractons, and particularly focusing on tensor gauge theories. And then I talked about quantum field theory of vortex lattice and the rotated superfluid, which is the message is it's a Wigner crystal plus process superfluid flow, which makes the crystal of vortices incompressible. It leads immediately through a Lifshitz model mapping to Tkachenko mode, single Tkachenko mode, which is quadratic. And then I described various mappings of that theory, and in particular, a vortex supersolid phase, a vortex supersolid phase, which is non-superfluid crystal of vortices. So with that, I'll stop, and thank you for your attention. You mean of this gauge theory? I haven't thought about it for this one. The more basic one for the ordinary tensor gauge theory for the crystals is 3. And so, let me think. It's been a while. Sorry, 4. It's 4, actually. Okay, just like ordinary abelian Higgs model. It's 4, but we have, and so part of the effort's been even for ordinary tensor gauge theory for the ordinary crystals. We've been trying to do the Halpern-Lubensky MAR and understand the critical properties around 4 minus epsilon expansion. It's been quite challenging, and we have not succeeded. So. This one I haven't even looked at because even I can't even solve the plain vanilla one. But that's an outstanding problem, in the subject. I don't know about the transitions, although, in principle, that's why I'm attracted to this. And again, forget vortices, just think about quantum melting of a crystal of bosons. It's really a fully, full description of that. It's a field theory that in principle in it has the, critical exponents of 2D quantum 2D melting. Okay, and so it's interesting to know, like, is it a priori? There's no reason it has to be first order, and And, you know, in principle, if there's a critical point, which we haven't found, you know, that's one connection to experiments. You know, you would be making predictions about critical exponents. There was another point I was going to make, but I lost it. So. Can you say it again? Can you repeat? You mean which intermediate? There are a couple of intermediate ones. I don't know. Oh, right here, this guy. Yeah. Right. It's hard to imagine because in this phase, you've unbound dislocations. But once the dislocations are unbound, a pair of them, B minus B, is a vacancy in interstitial. So in other words, in this phase, you have, if you wish, proliferation both of the, you know, single charges and dipoles. And so, I mean, you know, we know about deconfined criticality, for example. So there's no law of nature that I can cite that says that this must be, there's no way in even these complicated theories that to go continuously between vortex crystal and vortex exotic, but it's just strained because there's kind of two things, because I can imagine what can happen without unbinding dislocations and unbinding pairs of them. So you just, that's what that statement is based on, but it's not based on any concrete calculation.